Okay, welcome to Chapter 2. This chapter is on understanding the research literature. So we are at the step in the process where we try to come up with a research question based on a psychology topic. And so there are going to be a lot of articles that we are going to need to read in order to develop our research question and then ultimately a hypothesis that we will test doing research on human participants this semester. So we will go through kind of the major sections of the paper and what they are, and then we will also discuss some statistics, and but we're going to start with some tips on how to search for appropriate articles for your research project. So when you research existing literature, you're doing so at this stage in the research process to see what information on your topic already exists and to help you refine your research question and ultimately your hypothesis for the project. And that is, as we've discussed or will discuss in the lab, that process is a little messy. It's a lot of back and forth between searching the literature, coming up with an idea, searching the literature, refining that idea, getting inspired for another idea, and it's a lot of back and forth until you kind of hone in on the perfect research question. So when we are talking about literature in this course, we're talking about psychology literature, which is found in peer-reviewed journals only. And so the literature in those peer-reviewed journals are called articles. They are not popular magazines. They are not articles from newspapers. They are not articles that are found on people's blogs or Wikipedia, for example. So when we use the appropriate types of research articles for this assignment or for this class, the reason that we are choosing these peer-reviewed articles that are found in scholarly journals is because one reason is that they don't have any advertisements. So magazines and newspapers, they have to keep their advertisers happy. And so let's say you're doing a study and you find that Colgate doesn't prevent gingivitis, but the magazine that you write for advertises for Colgate. Then you have a little bit of a conflict of interest there. So we avoid that because scholarly journals do not have any advertisements. And another reason that we use the peer-reviewed journals or the peer-reviewed articles in scholarly journals are because they are, in fact, peer-reviewed. So what that means is that they are looked at by a panel of experts on whatever the article's topic is on. So if a researcher wants to study dreams and then write up a research paper on those dreams and submit it to a journal for publication, it then goes to all of the people that journal knows that are experts in the study of dreams. And then those people review the paper that was written by the researcher, and they do what's called a blind review. So they don't know the name of the researcher in case it's like a colleague or someone they've worked with in the past or someone they, had a bad experience with. And so they get this article with the author's name crossed out, and then they review it for accuracy, validity, reliability, all of those things. So the question is, can you use People magazine for your research in this course? No. Can you use New York Times? No. Can you use Dr. Laura's book on how to treat your husband? No. Psychology Today? No, you can't. You have to use the databases found at the library that are going to be a collection of these peer-reviewed articles that are found in the scholarly journals. So after you have found some articles that you want to review, you will notice that they are broken down into these sections that you see on your slide here. So all APA papers include an abstract, an introduction section, a method section, a results section, a discussion section, and a references section, and we will discuss more about those different sections over the course of the semester. But in short, an abstract is a summary of the whole article that you're about to read. An introduction explains what the hypothesis is, what the purpose of the research is. It explains what previous research says about this topic, and it explains how the researchers developed their hypothesis. And then that moves us into the methods section, where in our papers we present what we are going to do to collect data and how we are going to do that and what materials we are going to use. And then we move into the results section of our paper, and this is where you're going to find all the statistics. So in the study, data was collected on human participants, and then that data was analyzed with statistics, and they are all reported in the results section. So that's where we learn if the researcher was able to support their hypothesis or not, what their effect size was, all of that information. And then after that, we move into the discussion where the results section is kind of explained. So what were the outcomes? Was the hypothesis supported or not? Is that finding in sync with other literature? What do we hope to learn from this research? How can we apply it? How can we fit it into other theoretical frameworks? What suggestions might we have for future research on the topic? And also in the discussion section, we find any limitations of our current research in terms of like what we could have done better, for example. So all of that is discussed there, and then we move into the references page where we cite all of our sources. But when you are looking at those articles, I just want you to kind of notice the general format of an APA paper, because not only are the articles that you will be reading going to be in that format, but also the paper that you're writing for this class is going to be in that format. And so what we're going to do now is a brief statistics review just on a conceptual level. You're not going to need to do any calculations, but we are going to be using some stats in our research project, specifically descriptive stats, so measures of central tendency, variability, and correlations. So we're going to talk about those types of stats in addition to some other types of stats. Because statistics is a prerequisite for this course, you should have heard of all of these terms before. And these statistical tests. If some of them are new to you, that's okay. If you'd like more information on any of these stats, let me know. I also teach statistics, so I can give you access to my lectures in that course. But for the most part, you don't need to have a real in-depth understanding of the ins and outs of all the statistics for this class, because we're mostly just going to be focusing on central tendency, variability, and correlations. So the purpose of statistics is to summarize the data, and the data that I'm referring to is the data we're going to collect from participants in our studies that we're going to be conducting, and we're going to collect that data through survey methods. So we will be giving people questionnaires online, and their responses are going to become our data. When we have that data, we will use descriptive stats to summarize it. And then we can also use statistics to test a research hypothesis. So later on in this lecture, we'll talk more about a research hypothesis. And so if you are reading the literature and you come across some statistics that you're unfamiliar with, you could just go ahead and stop and Google them or send me an email. At no point in this semester do you need to try to pretend to understand advanced statistics that you've never heard of before, like hierarchical regressions or ANCOVAs or anything like that. So if you run across a statistic in the results section of a paper and you're confused by it, and you really need to understand how that statistical test works, which, I don't think I've ever had a student really need to know that. No one's ever reached out to me before about statistical tests. But if for some reason you really need that information, you need to understand a statistical test in a scholarly journal article, then let me know and I can help you with that. Or you could, of course, always Google or YouTube it. At any rate, here we go with our statistics review. Okay, and so now we're going to move into some basic statistical concepts. So there are two broad types of statistics. Descriptive statistics are statistics that summarize and organize scores from a research study. Basically, they abbreviate, summarize the data that we have. And some descriptive stats include percentage, range, mean, median, mode, standard deviation, variance. And so, for example, a descriptive stat would answer the question, what's the average age of students in this class? What you would do is you would go around and you would ask each student what their age is, and then instead of reporting that information as one student at a time, you could quickly report the information by summarizing it using a descriptive stat like an average or a mean, we call it, which is one number that kind of represents the whole data set or the whole body of scores or all the people's ages. So they're called descriptive stats because they describe a body of numbers or a data set or a group of scores, whatever you want to call it. Okay, and then the other broad type of statistics is inferential statistics. And so inferential statistics allow us to draw conclusions and make inferences that go beyond the scores from a research study. In other words, it allows statisticians to generalize what we find in a sample to the whole population. And so we can use just a small amount of data or a small number of people to infer characteristics about a lot of people or a larger group. For example, let's say that we wanted to find out the average age of students at SBVC and see if that age was significantly different from another college's age. We could do an inferential statistic that would allow us to compare those two colleges and see not only if there is a difference between the ages of, or the mean age of the students at the schools, but if that difference is significant. Is it a big difference or not? Is it statistically significant, we say. So, inferential statistics are where we do our hypotheses testing. So we make predictions and we test to see if those predictions are true based on what the data shows us. This can be risky, especially if you use a sample that is not representative of the population, or if you do your stats incorrectly. There could be potentially really negative real-world consequences for incorrect stats done in research. So we want to make sure that when we do inferential statistics, we do it as accurately as possible. However, we also do build into the statistics ways to identify and report any error that we have or that we are expecting because of just like the inherent problems that come with not being able to test everyone in a population. Or making mistakes or not accounting for all variables that need to be tested, things like that. So there's error in inferential stats. We know that. We account for it in our research. It's not a perfect type of statistics in terms of, or it's not a perfect science in terms of predicting or understanding human behavior. We can't say the word prove, for example, when we get our findings. We can just say if there are statistically significant differences or relationships between values, which in our case represent human behaviors, thoughts, feelings, ideas. So why do we even do stats if we can't use the word prove, if we can't say for certain that what we find in our sample is true of a population? Because the predictions that we make using stats are better than just guessing out of thin air, which we would call chance accuracy. And also with statistics and doing research this way, with inferential stats, we know what the limitations are and we acknowledge and report them. So it gives us a lot of information and helps us to better understand the world in which we live. So you're going to be learning a lot of different inferential statistics. They present themselves in the forms of statistical analyses. So they're tests that you will run to test your hypothesis, and they have different names like ANOVA, independent t, Pearson R, chi-square, paired t. These are all different tests. Okay, so we are going to dive deeper into descriptive stats, and we're going to talk about the three major types of descriptive stats that we will be using in this course, and they are central tendency, variability, and correlation. Okay, so central tendency allows us to kind of summarize what's going on in our data set with one number. In other words, how can a group of scores be summarized with a single number? The answer is central tendency. And central tendency is the typical or most representative value of a group of scores. And central tendency includes the mean, median, and mode. So we're going to learn about what they are now. So the first measure of central tendency is the mean. The way you calculate the mean is by summing all of the scores. Sum is another word for adding them up, and then dividing by the number of scores that you added up. So if you look on the slide, you see the formula there, and there's some statistical symbols and letters that we need to define. So if you see that one symbol that looks kind of like an E, that's called sigma, and it means summation of, or add everything up after me. So in this formula, it's telling you to add up all the x's. X stands for the raw score. So X is the score that you are collecting for your data set. N stands for the entire number of observations. Usually that's just the number of people that you have, is what we mean by observations. And then M stands for the mean. So if you look at the bottom right of the screen, you'll see an example there where they added up all 7 of those values highlighted in orange. They got 32, and then they divided 32 by the number of numbers they had just added together, which was 7. So 32 divided by 7 gave them a mean of 4.57. Notice how it is rounded to the second digit after the decimal. The mean is the most stable measure of central tendency because all the scores in the distribution are included in its calculation, which, as you'll see coming up, is not true of the mode or the median. The mean is used with equal interval variables, and equal interval variables just means that there's an equal amount between each number. So the distance between 1 and 2 is the same as the distance between 2 and 3, 54 and 55. So equal interval variables are things like age, weight, GPA. The next measure of central tendency is called the median. The median is symbolized there with a MDN, and it's the middle score in your distribution. So what you have to do is distribute all your numbers from highest to lowest or lowest to highest, and then you just identify the scores or score in the middle. If it is an n that is an odd number, then you're just going to have that one score in the middle, and that's going to be your median. But if your n is an even number, then you're going to have 2 numbers in the middle, and you would have to calculate the mean of those 2 numbers. And the answer that you get there is going to become your median. So if I had 50 and 50 as my 2 numbers, I would add 50 plus 50 together, get 100, divide by 2, because I used 2 numbers in my calculation, and I would end with 50. It's possible to get like 45.5 or whatever. All right, so it is better to use the median than the mean if there are extreme scores, which are also known as outliers. You can kind of get a understanding of what I'm describing if you calculate the mean, median, and the mean and the median for those scores. If you calculate the mean and you include all 5 of these scores in it, you're going to also include that outlier of 2.32, and that is going to positively skew your data to the right because that outlier of 2.32 is pulling the mean towards it. So the mean is going to be a higher number than the majority of the numbers there. It's going to be like 1 point something. I can't remember. You'll calculate it. You'll see, right? So add them all up, divide by 5. It's going to be a number that's 1 point something, which is not representative of the majority of the data there, right? Most of the data is less than 1. So a mean that's over 1 is really not representative. And so we want to use the median when we have an outlier like we have here with the 2.32. So if we put them all in order, then the middle number is going to be 0.81, and that number better represents the majority of our data. So we like to use the median if we have outliers and also if we have rank ordered variables. So if we are ranking our variables in order, like first place, second place, third place, if you ask someone what's your favorite type of food, put these in order, and you give them french fries, pizza, and hot dogs, and they have to rank each one, we would use median to describe the central tendency of that measure. And the last measure of central tendency is the mode. It's symbolized by MO, and it's just the value with the greatest frequency in a distribution. So when you make your frequency distribution, you just have to find the highest number in the F column. find the associated score, and that's going to be your mode. It's also going to be the highest point on the histogram or the frequency polygon. In a perfectly symmetrical bimodal, so when it has two data points that are clearly scoring more than any other, in a perfectly symmetrical bimodal distribution, the mode and the mean are going to be the same. If the distribution doesn't look this way, then the mode is usually not representative of that data. So the mode is actually the least used measure of central tendency in statistics. It's used with nominal variables, so variables that are categories like gender, eye color, favorite sports team. When people are responding to your survey questions in words, you have nominal variables. We'll talk more about the different types of variables later. The main thing you need to know is the mode is the value with the greatest frequency in the distribution. So central tendency is an important descriptive statistic in all variations, the mean, median, and mode. And what that descriptive statistic or what those descriptive statistics tell us is about the similarity between the scores. They give us one number that best represents those body of scores. And so they do that by reporting the mean, median, or mode. What's different here is in variability, we're going to get numbers that tell us about the differences between the scores. So central tendency looks at the ways the numbers are the same, and variability looks at how they're different. And so some of the things that variability can help us sort out is how spread out are the scores in the distribution, also how close or far from the mean are the scores. And so, like I said, there are three measures of variability that we're going to be learning: range, standard deviation, and variance. Okay, so the first measure of variability we're going to discuss is the range, and the range is symbolized by R. All statistical symbols are reported in, professional polished APA papers as italicized symbols. So that's why I have that R symbolized so that it's representing a statistical symbol. But anyways, the range is the measurement of the width of the entire distribution. And to calculate it, you just find the highest value in your distribution and subtract it from the lowest value in your distribution. So you can see the example here on your screen. The highest value in that distribution is 8 and the lowest is 2. So you just take 8 minus 2 and you would get your range of 6. This doesn't tell us a whole lot, just kind of a crude measurement of the distribution, but it's really the least useful measure of variability. Range is the least useful measure of variability in the same way the mode is the least useful measure of central tendency. Whereas the next measure of variability that we're going to discuss, standard deviation, is the most useful measure of variability. Standard deviation is the most useful and most used measure of variability, and that is analogous to the way that the mean is the most used measure of central tendencies. At any rate, the standard deviation is symbolized as SD, and it is a measure of variability that tells us the average amount that scores in a distribution deviate from the mean. Like I said, it's the most common descriptive statistic for variability. Standard deviations are never less than 0 because you can't have less than 0 variability. So it's important that you understand two things about that. The first is that if you do a standard deviation calculation and get a negative number, you have done your calculation wrong. It is impossible to get a negative number. The other thing that you should note from that is just the idea that you can't have less than 0 variability. The reason you can't have less than 0 variability is because things either vary or they don't. There's no such thing as negative variance. So if I am 39 and you are 29, then the variance between our ages is 10. There's never going to be a scenario where the variance between our ages is negative 10, say, because ages either vary, either, I'm older than you or I'm younger than you, and there's a variance there, or I'm the same age as you and there is no variance there. But there's nothing less than no variance. Okay, so as a reminder, the standard deviation is the average amount that scores in a distribution deviate from the mean. So think about what that means. If I get a score on my 50-point statistics test of 40 and the mean is 35, how am I within the average that people varied from that mean? Because not everybody scored at that mean, right? Not everybody got 35 on the dot. There's a variation in the scores. They're all over the distribution, right? So if I'm not right at the mean, then how far away from the mean is still like normal? What's like the normal range, right? And so that's what standard deviation tells us. If you look at your screen there, you see the normal curve, and in the middle is the mean. And so you see the two portions next to the mean blocked off in dark blue, and those portions are both one standard deviation away from the mean. And you can see there's a percentage inside of those dark blue portions, and that percentage says 34.1%. So 34.1% of the people scored between the mean and one standard deviation. And then also 34% of people scored one standard deviation below the mean. Okay, so what we're able to figure out is how many standard deviations people are away from the mean. So variance is the next measure of variability we're going to discuss. Variance is symbolized by a V, a capital V, and it's the measure of how spread out a set of scores are. It's also called the mean square deviation because it's the average of all the squared deviations from the mean. The variance is equal to the standard deviation squared. Sometimes students ask me if the variance is just the square root of the standard deviation, why would we use it? And the answer is that some formulas require using the variance rather than the standard deviation. Okay, so those were the measures of variability, and now we are going to kind of switch gears and talk about the two different types of hypotheses that we can test when we do our studies on human participants. So a hypothesis of association is the relationship between two sets of variables. We want to examine them to determine if these two variables are related or associated or correlated in any way. So as one variable goes in this direction, what does the other variable do? And that's really all that a correlational test can tell us, because as you know, with correlation, we cannot determine cause and effect because we're not including all of the variables. We're just looking at the relationship between two variables that we think can be involved in a behavior or whatever it is that we're looking to study. So another thing to remember about hypotheses of association is that when we do correlational research on them, the correlational research is post facto, meaning it's after the fact or after the IV has already occurred. So with hypotheses of association, the independent variable is not manipulated by the researcher, but instead it is assigned. So what that means is the participants come down to our study already containing the variables that we're looking to study. So if they are people who suffer from anger issues, we're not doing anything to manipulate them or manipulate their situation to invoke anger. Instead, we're asking people, do you have anger issues? Okay, we would like to assign you to our study because you already have that characteristic. So that's what is meant by assigned variables, and those are the kind of variables that we can study in correlational research, as opposed to studies that would employ testing a hypothesis of difference. So a hypothesis of difference involves the deliberate manipulation of a variable to see if a difference in behavior occurs. So when you're testing a hypothesis of difference, your independent variables can be assigned or manipulated, and you are also able to determine cause and effect relationships with the experiment because of the control you have over the variables and the multiple groups. And all of the different experimental elements. Okay, so now we're going to take a deeper look at what a correlation is. So a correlation is a measure of the relationship between two variables, and when you do a correlational formula, the result of that is going to be a value, a number, and that number is symbolized by an R, as you see there on the slide, a lowercase r. And that number is called a correlation coefficient. So again, a correlation coefficient symbolized by R is a number calculated from the formula for measuring a correlation. And there's going to be two correlational tests discussed today, a Pearson R and a Spearman R. So when you do that test and you end up with your R value, or as it's known, a correlation coefficient, it's going to give you an indication of the strength and the direction of the relationship between your two variables. So that value is going to range from -1 to +1. And you would know that you have a strong relationship between the two variables you're investigating if that correlation coefficient, that value you get from doing your formula, is close to a +1 or a -1. So knowing the relationship between our two variables can actually allow us to make predictions. If you study X amount of hours, a score of X is predicted. But at any rate, when you do your correlation formula and you get that correlation coefficient, it's either going to be positive or negative, or it rarely happens, but theoretically it's possible that you could get a zero correlation. So let's go over what those different terms mean. So a positive correlation is going to let you know that you have a positive relationship between your two variables. So that would be represented by a positive number. So when you do your correlational formula and you get a positive number, you know that you have a positive correlation. And what that means is that your two variables are in a positive, loving relationship. As one variable increases, the other variable also increases. But because they're in a positive, happy, loving relationship, they are also kind of together, Bonnie and Clyde, ride or die style. So in a positive correlation, if one variable decreases because those two variables are in love with each other, ride or die, the other variable decreases as well. So positive doesn't mean that they're both increasing. It means that they're both going in the same direction. So as one variable increases, the other increases, and as one variable decreases, the other decreases in a positive correlation. And then we have a negative correlation, which would be represented by a negative number. And so with a negative correlation, you can think of it as your two variables being in a negative, bad, horrible relationship, and they just can't wait to break up. So as one variable goes in one direction, the other variable is like, get me the hell away from this first variable. I hate it so much. I can't wait to break up. And that variable goes in the opposite direction. So negative correlations are when one variable increases and one variable decreases. And then it is also possible to have a zero correlation, which would be represented by a correlation coefficient or an R value of 0. And what this means is that there is no relationship between your two variables. So you might get like a zero correlation if you looked at the relationship between study time and height, for example. And then, as you know, the main thing to remember about correlation is that correlation is not causation. And this is because correlation does not tell us about cause and effect because of all those unaccounted variables that we haven't considered. All we look at in a correlation is just to see what two variables do when they're in the same space and or time together. However, it's important to note that it is possible to get a correlation coefficient above 0 that really is meaningless, and you just got a value by sheer coincidence. For example, if I see a black cat and I fall down the stairs, those two things are not related whatsoever, but I might get a correlation coefficient for them because they did occur in the same time and space. However, it was just complete coincidence that those two things happened. And they're not actually related to each other in any meaningful way. So we can represent our data visually using scatter plots. And the way that the scatter plot takes shape will kind of be a visual representation of if you have a positive correlation, a negative correlation, zero correlation, or what's called a curvilinear correlation. So we'll start with a positive correlation. If you look on the slide, you see that the top left square is representing a positive correlation, and you see the correlation coefficient in there. It says R equals 0.82, we'll call it. And so that is indicating to me that there's a pretty strong positive correlation there. I know it's strong because generally we have a rule. I'm going to show you Guilford's interpretation of correlation coefficients. But the general rule on the statistics streets is that a correlation coefficient of 0.80 or higher is representative of a strong relationship, and the same with a negative correlation. Negative 0.80 or higher would be considered strong. So I know I have a strong correlation here. I know it's positive because the R value itself is positive. And so if I look at the scatter plot, I can see all those blue dots, which you can think of as individual people's scores. I can see all those blue dots there, and they seem to be kind of trending upward in a linear or line shape. And then if I read what the x-axis and y-axis labels are, it says study time and exam scores. So because it's a positive correlation, I know that these two variables are moving in the same direction. So as study time increases, exam scores increase, and vice versa. And then we have a negative correlation to the right of that, and I look at the R value there and see that it's 0.63. I would say that that's a moderate correlation in terms of strength, more on the weaker side. I probably wouldn't publish any results with that correlation coefficient unless something really interesting was going on there. But at any rate, what this tells me, another thing to note is that if you look at the strength of the negative correlation versus the positive correlation, you could see how the blue dots are clustered tighter around that, we call that a regression line, that line that goes through them. The blue dots are clustered tighter around that regression line. So if it was a perfect relationship, a 1 or a -1, then those blue dots would line up on that regression line exactly. So it'd be a perfectly straight line. But if you look at the negative correlation, you can see that the blue dots are scattered further away from the regression line than in the positive correlation. And so I can visually see a weaker relationship represented there than in the case of the positive correlation as well. But I know this is a negative correlation because I have that negative R value. So what that's telling me is that as one variable decreases, the other variable increases. And in this case, those variables are exam scores and party time. So what this negative correlation is showing me is a kind of moderately weak linear correlation. They're all kind of moving in that downward line there around that regression line. So this would show me that as party time increases, exam scores decrease. And so if I made a scatter plot and it took that shape, I would be expecting to get a negative correlation when I run my formula. And then if you look at the bottom left, you see a 0 correlation there with exam scores and height. Does not take a linear shape. There's no clear pattern. It's just kind of all splattered there on the scatter plot. And then to the right of that image, we have a scatter plot with a curvilinear shape. And so what's going on here is that the data is trending upward, and then it's leveling off and kind of trending back downward. And so an example of this would be the Yerkes-Dodson law, which talks about performance and anxiety. And so if you look on the slide, you see that with a low amount of anxiety, performance is also low. And then as anxiety increases, performance increases. There over the moderate level is kind of its peak. And then after that, it starts trending downward. When anxiety gets really high, performance starts going down. So that is what the Yerkes-Dodson law suggests, is that a moderate level of anxiety is going to give you your best performance. Low anxiety is kind of like you're just not interested enough to be motivated to perform well, and high anxiety is maybe you're so anxious that it's distracting your brain from being able to function properly, and that would also affect your performance. All right, so shifting gears, those were the descriptive stats where we want to describe our sample and maybe test a hypothesis of association. And now we're going to be discussing inferential statistics in more depth. And so those concepts are going to include a discussion of what the null hypothesis is, what significance is, and what some common statistical tests are. We will be doing a correlation for our research project. That's the statistical test that we will be running. But we are going to review some of these inferential stats. And just briefly to kind of summarize inferential stats, If we want to generalize our results from a sample to a population, this is when we're going to be using these types of inferential stats. Since we realistically cannot test everyone or generalize to everyone in a population, we can only make an inference based on the data that we collect in our study. So inferential statistics are always attached to probability estimates. In other words, we don't use the word prove. We just say that what we found for our sample is probably true of our population based on these inferential statistical tests. And so we are also able, just like with descriptive stats, we can test a hypothesis of association. With these inferential stats, we can do the same thing, and also test a hypothesis of difference. So as long as we attach a probability statement, which we'll talk more about coming up, then we are able to infer from a sample to a population using these statistical methods called inferential statistics. Okay, so let's talk more about these hypotheses. But there's a weird thing about the way we test hypothesis in the social sciences, and that is that we don't test our actual hypothesis. We test what's called the null hypothesis, or the hypothesis of no difference. The hypothesis of nothing to see here, which means there's no difference between the sample and the population, or there's no difference between the control group and the experimental group, or a null hypothesis can mean there's no relationship between your two variables if you're testing a hypothesis of association. But we hope to reject the null hypothesis. Now, our actual hypothesis is called the alternate hypothesis, and it's symbolized by HA, or some people symbolize it with H1 as the subscript. So let's say that my alternate hypothesis is that I think my daughter is smarter than everyone else. And so we could say my daughter is the sample and everyone else is the population. And we know the population mean for IQ is 100. So I'm thinking that my daughter is going to be significantly different from that IQ of 100, probably like 140 or something. The alternate hypothesis is the hypothesis of difference that says the sample means deviates enough from that population mean. My daughter is, her IQ score is far enough away from that average IQ score of 100 that I can conclude that the sample, my daughter, is not from the population of people with an average intelligence. Or I could look at the alternate hypothesis as a hypothesis of association, but either way, when I reject the null hypothesis, by default, I'm accepting the HA, or the alternate hypothesis. So why would we do that? Why wouldn't we just test our actual hypothesis? And the answer is because we want to do our hypothesis testing as unbiased and as objective as possible. So rather than me going into my study saying my daughter's going to be smarter than everyone else, which could, if that's my attitude, it could consciously or unconsciously bias the way I select my sample, or bias the way I interpret the data, or even calculate through the data. And so I want to go into my study as unbiased as possible, and that's something that the HO, or the null hypothesis, allows us to do. So in order to reject HO, then, the statistical test value, the number you get from doing your statistic, must fall within the 0.05 or 0.01 critical areas. And using the previous example, let's say we did reject the null hypothesis, which in turn means that we accepted the alternate hypothesis. Then we must now say how unlikely our null hypothesis is. So instead of saying it is highly unlikely that there is not a difference between the sample mean and the population mean, or instead of saying it is highly unlikely that our sample mean is from our population, we would say there is a significant difference between the population mean and the sample mean. Or we could say the means of the sample mean and the population mean have found to be significantly different. In other words, the probability that the groups are the same, or that the sample mean is from the population, is very, very low. And so you might be asking, well, how low is very, very low? And that would be when the probability that the groups or means are the same is less than 5% or 1%. In other words, there is less than a 5% chance that these groups, the sample and the population, are the same. And so significance levels are called alpha levels or critical values and are represented by alpha symbol. So there's the little A, kind of curly A, or they're represented by p-values. And so this is how we normally represent them. So when we reject HO, we are saying we reject HO at either the 0.05 or the 0.01 level. And again, if you report P less than 0.01, that means that the statistical test value, the number you get from doing your statistic, fell in that area of the tails of the curve. And verbally, you would say that there is less than a 5% or less than a 1% chance that these groups, the sample and the population, are the same, that there's not a significant difference between them. So the way that you decide which statistical test of significance you are going to run is really determined by your hypothesis as a researcher. So that's why for our class, we are going to be doing a correlational hypothesis and then running a correlational test, like a Pearson R or a Spearman R. But there are some other tests that you could run if you wanted to test a hypothesis of difference as a researcher. So some of those other tests are t-tests, chi-square tests, and ANOVAs. So if you wanted to compare the means of two groups, often that's an experimental group compared with a control group, you could do a t-test. And so you are testing a hypothesis of difference, that the experimental group will be different than the control group. And so you can't just look at the means and compare them, because the t-test takes it a little further and considers the variability in the data. So it tells us about the statistical significance. Not only are these two groups different from one another, but are they statistically significantly different from one another? And then we could do a chi-square test, and a chi-square test tells us if there is a difference between frequencies we would expect versus frequencies that we observe. So the purpose of this is to determine whether a simple count of something, which is the definition of a frequency, differs from what we would expect to get just by chance. So for example, if I said to you, out of these 4 types of candy, Reese's, Snickers, Gummy Bears, and Almond Joys, which one is your favorite? If we asked 100 people that question, since there are 4 options, the frequencies that we would expect to get for each one of those options would be 25. So we would just take our sample of 100 people and divide it by the number of options we have, the 4 types of candy, and we would expect that 25 people pick Reese's, 25 people pick Snickers, 25 pick Gummy Bears, and 25 pick Almond Joys. But when we do the chi-square test and we get our actual data, then we would compare it with what we would expect to get just by chance and see if there's a significant difference there. So if there was a candy that was just like off the chain, I don't know what candy's off the chain, like Rolos. Rolos are really good. And so everybody preferred Rolos over, or the vast majority of people preferred Rolos over the other options. Then we would have a significant difference between what we expected to get, which would be, out of 100 people and 4 options, we would expect 25 people to choose Rolos. But if like 75 people chose Rolos, then we would have a significant difference between what we expected to get and what we actually got. And then we have ANOVAs, which are kind of like t-tests, except that instead of comparing 2 groups to see if they are significantly different from one another, ANOVAs compare 3 or more groups. And then the tests that we are going to be running for our class are either going to be a Pearson R or a Spearman R, so it depends on how you collect your data. Generally, my students end up doing a Pearson R because I encourage you to use continuous variables. And so continuous variables are variables that are quantitative, so they're numbers, they're numerical, and the numbers are considered continuous because they could go on forever, and there are equal intervals between them. So examples of continuous data are going to be things like the amount of money you have in your bank account. So the difference between $1 and $2 is the same as the difference between $2 and $3, and you could essentially have an unlimited amount of money, if you're super duper rich. So that's a continuous variable, and that's what we're going for, versus like a categorical variable, which would be like the example that I used with the different types of candy, where you're choosing a name, like nominal data, a category of something. And so, in other words, if you're collecting the data in words, then you're most likely using categorical data. But if you're collecting numbers from your participants, and these could be things like the like response scale of 1 to 5, that counts as continuous data. So if you ask someone on a scale of 1 to 5, because in theory you could do the scale from 1 to 7 or from 1 to 10. You're just the one setting the limiter, but it is still continuous data. So if you wanted to ask people on a scale of 1 to 5, where 1 represents strongly disagree and 5 represents strongly agree, how much do you love Ryan Gosling? And they say 5, that's going to count as continuous data. And that's pretty much how we're going to go about collecting the continuous data for this class, is by writing items and then asking people to agree or disagree with those items numerically. So when we use continuous data, we can use a Pearson R, and specifically we need interval data, which is, as you know, numbers. And so if we want to do Spearman, then we would need to have ordinal data, which is data that has been ranked. And there are special circumstances when we would want to use that type of data. It just depends on our research question. And of course, I would help you with choosing between a Pearson R and a Spearman R. But what you can do from this point forward is focus on, coming up with this research question and kind of whittling it down over the course of this week, and into one that is really workable for this class. And so one of the things you need to keep in mind for a workable research question for this class is that it needs to test a hypothesis of association. It needs to have continuous variables. And so because it's a hypothesis of association, you would be looking to see if there was a relationship between two continuous variables. And that is it for this lecture. Thank you for listening. Have a great day.